Welcome everybody. Today we're going to talk about a community challenge that we have put together with a great team of researchers across the country to really create a common database of cases for machine learning research for fluid mechanics. So come with me, so I'll tell you more about it. What we are doing, and I want to mention everybody, we have Oliver Smith, Aaron Town, Adrian Lozano Duran, and Scott Dawson from UC San Diego, University of Michigan, Caltech, and Illinois Tech in Chicago. What we have put together is this challenge with actually 3 different cases where we can try different methods and we can actually compare different approaches. And this is part of the AIAA. So we have the paper, which will be out very soon in AIAA. You're going to have the reference to the archive so you can see all details. And in a nutshell, we have 3 challenges. One on compression, one on forecasting, and one on sensing. You can see a little vignette here of the different cases, but I'm going to tell you a bit more when we go through the next slides. So also here at the bottom, you can see the email of the organizers and also the website. So if you want to learn more about the different approaches, about the different benchmarks, and also if you want more information about participating in this challenge, then feel free to reach out anytime. First challenge has to do with compression. And down here, you can see the reference in archive. So you can actually check out the paper for full details. In general, what we want to do is to reduce the size of the data that we are storing. We focus on turbulent flows, and we're going to consider different methods such that we can really see how different approaches to reduce information, to compress, they work, and how well we can actually reconstruct the original data set in our data. So let's talk about challenge 1.1. Each challenge has basically 2 sub-challenges. So the first one in this case is compression of 2D boundary layers. So here you can see a little description of the challenge. So you have different snapshots in 2D. So this is taken from a big data set where we just have a vertical cut of turbulent boundary layer data. And the idea is to compress this data as much as possible and reconstruct with the highest possible accuracy. Now, there's several things that are important for this problem, and here you can see different metrics. The latent dimension tells me how well I'm actually compressing. So if I have a few variables in the latent space, that means that I have been able to compress very well, because each of those latent variables contains a lot of information. We also want to look at the reconstruction error. So we want a low reconstruction error, and we also want a pretty good speed of implementation of this framework. So we want to look at the various metrics, and of course, ideally, we want something that is very fast, reconstructs very well, and has a pretty low latent space, so a very small size. And we are having what we are presenting in this community challenge is basically vanilla cases. So we have results in this slide about a very simple autoencoder, which is basically a nonlinear deep learning based compressor, and POD, proper orthogonal decomposition, which is probably the most famous linear way to compress turbulent flow data. So you can see some of the results here. I mean, the autoencoder, because it compresses non-linearly, typically can get you to a smaller latent space for better reconstruction, and is typically slower than POD. So that's kind of like the trade-off that you can see here. Now, the results that you will find in the paper and that I'm summarizing here today, these are basically vanilla cases. These are very, very simple baselines. We want you guys to really try to beat these cases, these baselines, and get the best results possible. So this is the minimum that you can do. We want you to try to do better than this. There is a second challenge within compression, and you can see here a little description. You have all the results in the paper, which is the compression of 3D boundary layers. So in this case, we have 3-dimensional flow fields, and the idea is the same. You want to be able to compress with whatever method that you want to choose This is linear, nonlinear autoencoders, any model decomposition, any algebraic decomposition, whatever you want to do. In this case, the data is going to be 3D, so larger and more challenging. We want you to be able to compress as much as you can. Challenge number 2 has to do with forecasting. So what is forecasting? The idea is that we want to predict future states of a system based on the present knowledge, or even including some of the past knowledge of that system. Why is it interesting? Well, first of all, if we want to do control, so if we want to do flow control, being able to predict what the system will do and how the system will be modified under certain actions is helpful. And the other one is computational speed up. So if we can develop low order methods which are cheaper and we can forecast those in time effectively, that gives us a pretty good, strong reduced order model which can speed up our predictions and our design choices. So basically combining a good compression, challenge number 1, with the good forecasting, challenge number 2, allows us to get pretty good reduced order models. Now, the first half of this challenge, challenge 2.1, is forecasting a turbulent cavity. So basically this case that you can see here. And so you just want to, given some time series which determines the temporal evolution of our system, I want to predict the future evolution of that system. And this is what the results look like. This is interesting, and I'm showing you basically 2 methods. I'm showing you here a metric of the error, where on the one hand you have DMD, so that's dynamic mode decomposition. This is a linear method based on model decomposition to try to forecast in time. And the second one is the long short-term memory neural network. And you have seen a lot of this in my channel and in many references. So the LSTM, the long short-term memory network, is a vanilla architecture for temporal predictions. It's a bit more, a bit more suited, a bit better equipped than the multi-layer perceptron for temporal predictions, but it's still a very, very simple method to predict in time. And as you can see here, a vanilla implementation of the LSTM and a vanilla implementation of the DMD, they work similarly. At the beginning, the DMD has a slightly higher error. Towards the end, the LSTM has a little bit of a higher error. Once again, these are the baseline. These are the simplest cases. I want you to try to do better and come up with more sophisticated approaches to model time. And remember, these cases, these flows, are typically multi-scale, so that's something that you want to keep in mind when setting up your cases. The second part of this challenge is a little more complicated. Challenge 2.2 is forecasting a pitching airfoil. So here, same idea. You have some temporal information. You want to advance that in time and get a pretty good idea of the temporal evolution. In this case, a pitching airfoil, which would be 2-dimensional data, so a bit more challenging, but in a way conceptually very similar, being able to exploit temporal dependencies in your data to predict in time. And challenge number 3 has to do with sensing. The goal here is to reconstruct the state of the whole flow or part of the flow from partial measurements. So basically, can I measure somewhere, and based on those measurements, can I predict the flow in other places or everywhere else in principle? Of course, this is helpful for experiments, digital twins, and flow control. So being able to estimate the state of my system, being able to fill in the gaps of what I cannot measure in the experiment is always very helpful. And the first half of this challenge, challenge 3.1, is basically the, time resolved jet measurements. No? So basically this type of problem where I have a bunch of sensors from this 3-dimensional flow field that you can see here, and I can estimate the evolution in time. So I want to be able to reconstruct from sparse measurements in my jet the rest of the flow field, which I don't have access to. And in terms of the results, we compare, this is at 2 locations, the jet center line and the jet lip line. And we have a linear filter, the winner filter. And then we have 2 different MLPs, multi-layer perceptrons. On the one have a linear MLP, which would be actually analogous to a linear method, like a PCA, for example. And then a nonlinear MLP, so basically an MLP with a nonlinear activation function, in this case, the hyperbolic tangent. And you can see that the error metrics are actually pretty similar. As before, the linear method starts to be, at the beginning, quite similar to the nonlinear ones, and towards the end, the winner filter works a little bit better. Once again, keep in mind that these are baseline results, and the idea is that we want you to try to do better than this. The second half of this challenge is sensing in a turbulent boundary layer from the wall. So the idea is that you will get wall shear stress measurements from a DNS, from a direct numerical simulation, and want you to predict the flow at y plus 15. So the streamwise velocity fluctuations at the near wall peak, as you can see here. Remember that in this case, we have spatial information that we can exploit. So try to use methods that can exploit the spatial information. You will see in the paper that we use a very simple CNN, convolutional neural network, to make this prediction. I'm sure that you can come up with something that is more effective at capturing those scales in our flow to try to beat this basic baseline. And that's all we had today. I am very happy to present this community challenge for everybody. This was a fantastic collaboration with University of California, San Diego, University of Michigan, Caltech, and IIT. Fantastic authors. Feel free to reach out to us. Once again, you have here the website of the challenge and the email. So you will find all the information there. Feel free to submit your responses to this challenge. I'm happy to answer all your questions. See you next time. Bye.